Hello and welcome to podcast number 28. This starts a whole new chapter and quite honestly, kind of a whole new approach to OChem. So everything to this point has been kind of a buildup of rules that we're going to apply. In some cases, just review of general chemistry that still applies to OChem. But now we're actually setting course on things that are specifically OChem. And we'll figure out why we worried about RNS, for instance. It's going to play a major role in this. Why worry about meso and enantiomers, diastereomers. The reactions we're going to do are going to generate products that will be either structural isomers, stereoisomers, or achiral. And these are things we're going to have to figure out as we go. So this chapter, it's going to be, I'm assuming, 5 podcasts total, is going to cover all sorts of reactivity. So it's going to be daunting at times, but it still follows all the basic rules of chem. And that's the goal of everything we've done up to this point. So I want to start with just the concept of a nucleophilic substitution reaction. So a lot of these words you've learned along the way. A nucleophile is the molecule or the reactant that carries a lone pair that donates in. Typically, they carry some sort of partial negative or negative charge. They donate those electrons to a carbon atom that carries a partial positive charge. And in doing so, they create a new bond, which will almost always require a bond being broken to make room for it. So I'm going to start with simple cases and just define what the terminology is. I also want to apologize. My throat is in wretched mode, so I'm going to try not to cough and yak. But keep in mind, these are the not so professional videos. These are just ones to cover what we're going to do in class before we do it. But substitution, we mentioned in a previous lecture, was one group, we'll say this one, going on, and then another one, say this, coming off. So it's just the pathway of how this occurs. So we're going to worry more about not just what's happening, but this chapter we're going to worry more about how it's happening. Let's at least get all the pieces labeled. Called a substitution reaction because we're substituting one group for another group, or in this case, one group for an atom. So there's our nucleophile, and it is going in to the carbon and forming the new bond to carbon. And then here's our leaving group, as it's called, the one that's get kicked off, so the one that's coming in. So this one comes in, substitutes for this one. And as I alluded to in some of our previous podcasts, whether this comes in first and kicks this out, or whether this leaves first and then this comes in, that's going to be pretty significant in terms of the end results. The other thing that's going to become important is how it comes in, which direction. And so if you have good instincts for physics, there's something called conservation momentum, where if I come in from the left, I will knock the ball that I hit out to the right. So when it hits that ball, I have a couple options. The two may move together, or the initial one will come to rest, and this one will move. So I should color these in to distinguish what's happening. So it comes in, and it can either stick to the other one, they'll move together, or it can come in, and it comes to rest, and the other one moves. We're going to focus on this one, where one comes in, the other one goes out, but it's called conservation momentum, meaning we always want to come in. So if I want to knock this one off, I need to come in from what's called the backside. So we'll go into more detail on that as the time comes. But substitution, we're going to get into a few more details. But for now, a CN group, a cyano group, is going in and substituting for a chloride. Okay, so we're going to refer to this as a nucleophile. It's the one going in. It's one donating the lone pair of electrons. So the lone pair on carbon is going in. So this is acting as a nucleophile. This is acting as a so-called leaving group. It is leaving the molecule. So nucleophile is the participant in the reaction, the reactant. It donates electrons to electron poor partially positively charged carbon. The electrophile is the entire molecule that's receiving the electrons from the nucleophile. And then the leaving group is specifically the atom or group of atoms that experience a bond breaking and become independent of the original molecule. Okay, we are big on words, but hopefully this makes sense. Something comes in, kicks something else out, and the new molecule forms whichever way it forms. Okay, so moving into specifics. Have to decide whether something's going to be a good or a bad nucleophile. So a couple ways we're going to do that. And one of the things that becomes imperative is to distinguish between when it acts like a base, i.e. takes a proton, which is positive, or a nucleophile, acts as an electron pair donor and attacks and forms a bond to a carbon that carries a partial positive. And so a couple of rules, couple things to consider. So in one case, the reactant is going to remove the most acidic proton on the molecule and leave it deprotonated, and thereby the base gets protonated, turns into conjugate acid. We've done that reaction. But in the other instance, the one we're going to focus on this time is that same group that comes in, like the CN minus in the last case, rather than pulling off a proton, it attacked and formed a new bond to the most partially positive carbon in the other reactant, the electrophile. So whenever I look at the two molecules, I'll recognize one as either electrophile or a proton donor, and I'll recognize the other one as either a nucleophile or a proton acceptor. So whether it deprotonates or attacks a positive carbon depends on the compound itself. So there's going to be a bunch of factors, but the basic gist is this. It is way easier to pick up a proton because they're so light. You just go and you grab a proton and you're on your way. So if it can, the molecule would prefer to act like a base if there's an H to take. So what we have to do in OChem, if we want something to act like a nucleophile, we need to make sure that there is no acidic proton that it can take. Otherwise, it'll act like a base first. So the preference is a base because it's lighter, easier. You grab it, you go. Not as challenging as a nucleophilic reaction. So when deciding whether something's a good nucleophile, we have to consider its basicity and some of the other factors that come into play, such as its size. So if it's a strong base, capable of pulling an H off a carbon, you want to go deprotonation. So fortunately, H's on carbon range anywhere from just below 20 up to 49. So they don't come off easily. So it's got to be an exceptionally strong base, like an OH minus is going to engage in deprotonation. Sometimes it'll be a nucleophile sometimes. But generally speaking, mild bases, medium bases, weak bases, if you will, typically, as a general rule, act as nucleophiles because they are not strong enough to pull the H off a carbon. So that is why I use CN minus. It's a conjugate base of a weak acid. So H stands for weak acid, CN minus is a weak base. We use ammonia or the amines because they are weak bases. So they have a tendency to substitute and not deprotonate. And so all that acid-base chemistry we did earlier on was really to introduce a bunch of potential nucleophiles for this chapter. So I'm going to go back and reference the pKa information we did from time to time. But it's basically, if you remember your 5, 10, 10, 10, 15, 20, 25 compounds, the deprotonated form of all those will range from good nucleophile for the conjugate of the weaker or the stronger acids will make weaker conjugate bases. So 5, the carboxylic acid, its conjugate, is going to be more apt to be a nucleophile than a base. The 10s, the amines, the thiols, and the phenols will typically, when they're deprotonated, be nucleophiles because they are, again, weak bases. But you start to get a little bit higher and higher, then you start running risk of things becoming acting like bases instead of nucleophiles. And again, we'll cover this as we go, but it's a good general rule. If it's too weak, can't deprotonate, can't substitute, you may get no reaction. That's going to be really rare. So we're going to classify as poor nucleophiles and good nucleophiles when we look at this. Okay, so good nucleophile must be basic enough to attack, but not so basic that it takes an H. So that's what we're going to mean by good nucleophile. So electrophiles, on the other hand, just like nucleophilicity is based on basicity, electrophiles are the ones that are the best Lewis acids. So electrophile must have a leaving group and a partially positive carbon. The bigger the partially positive carbon, in general, the more reactive it's going to be. So electrophilic carbon is host to the exchange of the nucleophile for the leaving group. That's something you'll see over and over and over. There's always a carbon that's getting something attacking it, and therefore breaking a bond to a leaving group off of it. So good thing to recognize, alkyl halides are very typical electrophiles. I'm going to use those over and over and over. So you notice the previous one I did an alkyl chloride. So I'm going to use those fairly often. So also want to note, and we mentioned this again, this is one of those structural components that we brought up earlier. So make sure you know what this means. Primary carbon is a carbon that only has one other carbon attached. Secondary has two other carbons attached. Tertiary has three other carbons attached. So in Rx, just one. That means the other two atoms I'm not drawing in are H and H. H's are small. So overall, this is a small molecule, particularly at the reactive center. So it's going to be easy to attack. So, for instance, propyl chloride on the primary carbon, highly reactive, or highly susceptible to what's going to be called an SN2, or nucleophile coming in directly and not waiting. Secondary. So here we have a carbon with two other carbons attached. So again, typical example, iodocyclohexane, excuse me. And then tertiary has three. That's where you start getting really, really crowded. So T-butyl bromide, for instance, be a good example. And so we notice this is easy to attack. This is harder to attack. So consequently, their reactivity is going to be different. And different in the sense that in one case, nucleophile is going to be able to attack and react with it instantly. This one, nucleophile is going to have to wait till something leaves to make room for it before it can attack. Excuse me just one moment. I'm so sorry for the lack of professionalism, but reality is I'm getting a little bit behind on the schedule for getting these up to you. So sorry you have to live with the coughs. Ranking nucleophiles. I like this, what I'm putting here. I like the fact that I'm just calling it a small list of organic molecules. This is a borrowed list from, oh, actually, next page will be the borrowed list from them. I'm going to say there's a massive list that we actually go through. By calling them R's, we make it a little more simplistic, but certain groups, if you have, T-butoxide is going to be the most common example we use. But if you have three R groups on a carbon with an O minus, so if I made something like this, one, a negative on an O is highly basic, like OH minus, but instead of an H, you have this. Number two, this is so large and so bulky, it's going to be hard for it to come in and attack the carbon as a nucleophile. So it usually settles for being a base. It'll pull a proton off. We also find that amides, when we deprotonate the nitrogen of an amine, we have R2 with two lone pairs and a minus. Again, if the R's are big, it's exceptionally favorable to be a base rather than a nucleophile. And then R minus. Just in general, whenever you have an alkene that you deprotonated, and somehow pull that proton off, it does not want a proton taken off, so it's such a strong base, it's going to deprotonate whatever it reacts with rather than attack. Okay. Our second grouping, the good nucleophiles. You'll notice their conjugate bases have pKs of 10, or I'm sorry, the conjugate base of an acid with pK of 10, slightly higher for thiols, around 9.5, so 10 minus a little bit. Phenol, the phenoxide, pK of 10, and HCN has a pK of around 9.2. So notice they all have pKs in the roughly 9 to barely over 10 range. That means they are all conjugate bases of weak acids. They themselves are actually weak bases because their pKv's are in the neighborhood of 3, 5, 5, and 4. So they still qualify as weak bases, so they're going to be great nucleophiles. So when you see these are ones you should recognize. Okay, nucleophiles will be your Cl minus, your Br minus, your nitrate, the conjugates of very strong acids. So even though they don't want to pick up a proton at all, they actually can attack. They're not great. They're very weak bases, but they still can react as nucleophiles. And then we're also going to toss water in that group. And so as we get more and more examples, you should keep an ongoing list. But this is a good starting point. It is worth your time on whatever piece of paper, or wherever you want to store it, make a list of poor nucleophiles because they act like bases, and then make a list of good nucleophiles and weak nucleophiles, good and okay nucleophiles. and keep an ongoing list. As mentioned, the size makes a difference. The smaller the nucleophile, easier it can go in, and the smaller the electrophile, the more it's receptive to something coming in. The larger the nucleophile, the harder it is for it to go in, or the larger the electrophile, the harder it is to make room for a nucleophile to come in. So this is going to impact whether it's SN1 or SN2, and to some extent whether it reacts. If you have a really large electrophile with a really large nucleophile, more likely to do an acid-base reaction than it is a substitution. But if they're really small for both of them, then substitution is reasonable. So what are the absolute best nucleophiles? We kind of named them. So this, and this. This one gets nixed because it's a little on the big side, so it doesn't quite qualify. And notice I used an H to make that minimalist. I used H's to make it minimalist, and this is small. So tiny, tiny, and tiny with PKBs of 5-ish, like 4.8 or so, and around 3 to 4. So they are weak bases, and they are tiny. It makes the very best nucleophile. So when you see any of these three, you need to immediately think something's going to undergo substitution. Okay, here's that small list I had talked about from before. And notice, put in the thing SN2 reaction. So we haven't gone into that yet, but that's a substitution where the nucleophile pushes its way on first and displaces the leaving group from the electrophile simultaneously. So the best nucleophiles, you'll notice, are, as mentioned, this. Ammonia is up there, and it's interesting it's down here. So I'll explain why as we go. But because we do multiple substitutions, and when it substitutes, it becomes positive, we start running issues. So it starts having to deprotonate itself. So this one, I'll leave it as kind of an open-ended thing. Amines, I'm going to actually think of as better nucleophiles than some of these other ones. But notice the great nucleophiles are here, here. This is one we're going to add as we go. It's going to be our surprise one. So I expect you to recognize that. And then the amines, but ammonia is listed a little bit further down. Those I want you to definitely recognize. Phosphorus is right below nitrogen in the periodic table. So if you replace nitrogen with phosphorus, it actually is a pretty good nucleophile. It's certainly not going to be a base. And then the halogens, notice I is the best, Br, Cl, and F is actually surprisingly not a good nucleophile. And you can change that depending on the solvent a little bit, but by and large, this is going to be our running list. Okay, I feel pretty good about this. This is kind of, it's not an absolute line, but it's still a pretty good one to go by. So water is a poor nucleophile, that you need to know, and alcohols are poor nucleophiles. Carboxylic acids are poor nucleophiles, but when you deprotonate them, OH minus is good. RO, alkoxides are good, and carboxylate. So these deprotonated end up pretty good. Okay. I don't expect you to memorize that list 100%, but as we go through it, I expect it to be so sort of programmed in as you see the same reactions over and over, you start recognizing good and bad. So early on, try to be cognizant of what a good or bad nucleophile is or where it ranks. And keep in mind that list is a rough estimate. As the R groups change, that list will fluctuate a little bit. So it's not a perfect list, but it's a great start. So if we considered from that list reacting with the same molecule, methyl iodide, that's my electrophile, I is my leaving group. According to that list, CN, the SAN group, was a better nucleophile than azide. So better means it's going to attack more quickly, it's going to be more complete. So in this case, I'm going to focus on faster reaction. I could also focus on which generates more product. But if I go by that list, SAN group's a better nucleophile. So as a result, we conclude SAN group is a better nucleophile than azide. Okay, so we have now the deprotonated thiol versus the chloride. Again, if this is R is really big, this isn't as clear. But as long as R is very small, and you can't get any smaller than 3 H's on carbon, so even if this got a little bit bigger, it still wouldn't matter. That's going to be your better nucleophile. And we celebrate with fireworks and happiness and joy. Okay. So Br minus versus phosphine. So this one, hopefully you recall, phosphines were really close to the top of the list. They're like an amine, So 3R groups donate in, make it more electrophilic, or more nucleophilic, excuse me, make it a better reaction with this electrophile. Okay, so better nucleophile in that case. OH minus versus, so this is where it gets a little interesting because RS minus is a good nucleophile. When you protonate it, it's not quite as good. It's not as willing to give up its lone pair. Whereas water is a terrible nucleophile. When you deprotonate it, it becomes an okay nucleophile. This one could potentially act as a base, but we're going to say when it acts as a nucleophile, this is going to be a slightly better nucleophile. And then finally, ammonia, which if it's an amine with R's, it's better. But if it's ammonia, just all H's, because it has tendency to pick up protons along the way, it ends up not being as good. So it's getting protonated hinders its ability to be a good nucleophile. So we end up with the deprotonated alkyne being the better reaction. So hopefully this is gives you some idea. Do not belabor this. Do not get too caught up in it because you can always reference the list. But this is one of those, just start getting an idea of where things fit within the reactivity chart. So notice the minus helps a bunch. It didn't in this case, so halogens kind of violate the rule a little bit. They're perfectly stable as minuses, so they're not going to be as nucleophilic. Azide, decent nucleophile, but still not as great as some of the other negative ones. And the neutral, like water, not a good nucleophile. Alcohol is not a good nucleophile. Protonated thiol is still an okay nucleophile. It's still technically on the lower end of a good nucleophile list, but better when it's deprotonated. Okay, a lot of information being thrown at you. Best way to handle a lot of information is starting to put it into a fashion, some form you can recognize. So maybe copy that list over that was just on there, the good nucleophile list, or give yourself a series of cards where you quiz yourself on it, but have an idea what good nucleophiles are and just like how you can test it. Faster reaction or more complete reaction, more product form. Okay, now I want to predict how good of a leaving group something is, because that's the other half of the reaction. Nucleophiles that come in, but a leaving group also has to electrophile to lose a leaving group for this reaction to go. So you have half it being the nucleophile coming in, half the electrophile leaving. So past behavior predicts future behavior. So really good example, if you happen to be an NBA fan who's old enough to have seen Dwight Howard with the Lakers and the Houston Rockets and the Atlanta Hawks and the Orlando Magic, and basically the 1,000,001 teams he was with in his career, you would note that in his first place playing, he was happy until another player came along, a guard who was really good, and then he sort of had a tantrum and demanded the team trade him, get rid of him. So he went from Orlando, where he was jealous of a guard, ended up in Los Angeles, which happened to have a guard, and after a year he demanded to leave because he was jealous of the guard. So what do you think happened as he went to each of these next few teams? Same thing. Moral to the story, your behavior in one situation predicts your behavior in future situations. So just as he didn't change, neither does X minus. And so what that means, sorry to make this a sociology class for a brief moment, but if something behaves in a certain way in one scenario, can we predict what it'll do in another scenario? So if this is a strong acid, that means X leaves from H very readily, then X must be good at leaving in general, which means it's probably going to be good at leaving from a carbon. Notice I put 3 R groups now, the crowded one, situation where it has to leave before anything can come and attack. So I'm going to use that as my typical example. So because HI is a stronger acid than HBr, RI is a more reactive electrophile than RBr. Just like HBr is a stronger acid than HCl, RBr is more electrophilic. RBr is going to give up bromine leaving group more than RCl will give up a chloride. And so we go through the typical strong acids, HI, HBr, HCl, sulfuric acid. Although this isn't sulfuric acid exactly, it's an organic equivalent, so it can go into solution, but it still has the SO3 with a group attached here and then something on the O. So just as a point of interest, this is a spin-off or an analog to sulfuric acid. Water is a great leaving group because H0 plus is highly acidic. HF, this is where the rules start to change a little bit because HF is not very strong acid. So F is not as good a leaving group, but we still put it in this list. And then OH is a terrible leaving group. So what I mean by this is where it switches, goes from very good leaving groups and to this point here, it turns into kind of a poor leaving group and a poor leaving group. So the relative rate is all true, but there's a huge drop off from very good leaving groups to terrible leaving groups. But the point of doing all that acid-base chemistry and knowing those pKa's, if you know the pKa, you can predict what kind of acid it is, and therefore you can make a correlation or a prediction on how good of a leaving group something will be. General mechanistic rules, things you have to know. So we typically view nucleophiles as coming in and attacking electrophiles, meaning we always draw arrows from where the electrons start, i.e. the nucleophile, to where they finish, the atom in the electrophile that's getting the new bond. So we're going to draw all our substitution reactions that way. So you've already done this to this point, but just want to reemphasize. We're always going to draw from the electron pair on the nucleophile to the carbon, the delta plus of the electrophile. Now I haven't drawn everything else in, but the minus is attacking the plus, pushing the minus on the other. Just based on electrostatic repulsion, it's not really going to come into the negative side because negatives will repel, so it ends up on the back side. But also, this is that whole conservation momentum. As this one comes in, it hits the carbon, knocks the leaving group out. Okay, so nucleophile obeys the conservation momentum rules, which we call backside attack. It comes from the backside of the leaving group. So both electrostatic repulsion, negative wants to be near plus and away from minus, so electrostatics play a role, and then conservation momentum. So basically, physics is explaining a little bit of our chem. So backside attack means it's going to attack from the backside of the carbon. Okay, so hopefully that seems okay. So I'm going to stop for this one. This is the introduction into the basics, what the definitions are. The nucleophile, electrophile, what you should do following this particular lecture is just have a fundamental idea of what a good nucleophile is, what a good leaving group is, and how to correlate it to pKa, and then just a general idea of what we're going to be doing as we get into these nucleophilic substitution reactions. So just want to say thank you for tuning in yet again, and I will see you at the next timecast. Bye.